Okay, guys, today we're going to explore Einstein's theory of relativity or special relativity and some of the implications it has, like time travel, for example. This is the setup. We have a laser with a mirror, and then we're kind of observing it. So that's the back of us observing it. So keep in mind as we look at this setup, we're the outside of it, we're observing it. Um, we're part of its inertial reference frame in this situation. So, for the first couple of examples, we're going to imagine ourselves and this lab equipment basically like in the same room. So, if you kind of imagine it that way, it'll be helpful. So, this is what we would see when we turned it on. Okay, the beam would go up towards that mirror, and if we set it up correctly at the right angle, it would reflect back down and hit this mirror sensor that's attached to the laser. When we turn on the laser, it starts the timer, and then when the beam comes back and hits that sensor, it stops the timer. So think about this for a second. If we wanted to calculate the speed of the laser beam, which would be the speed of light, what other information would we need? Okay, so we would need the distance from the laser to the mirror at the top. Let's say it's 1,500 meters, and the time, the round trip time, is 1.00 times 10 to the negative 5 seconds. Use that information, take a minute, and calculate an answer for the speed of the laser, which would be the speed of light. Okay, so distance over time, we know speed is measured in, for example, 60 miles an hour is distance divided by time. So we're going to use the round trip distance, 3,000 meters, divided by the time, 1.00 times 10 to the negative 5 seconds. When we do that, we'll get 3.00 times 10 to the 8 meters per second, which is the speed of light. Obviously, very fast. So let's take this setup and let's change it around a little bit. Let's take this setup and put it on a train car. Okay, we're still going to be observing it, but we're not going to be in the same room. So we're not going to be on the train with the setup. We're going to put the setup inside the train car and we're going to look at it. Okay, it's on the car. The car's in front of us. We're watching it. Nothing's changed. All right, let's get this train car moving. So let's have it move really fast and let's see what happens. So this video, watch this for a minute, I think gives another good example with a ball being thrown straight up on a train. So let's watch this for a second.
Relative. Imagine you are sitting in a moving train. You toss a ball into the air and catch it. To you, the ball went straight up and down. But to an observer on the ground, the ball followed a parabolic path as the train went past. This is because when the ball leaves your hand, It still has all of the forward velocity that the train does. But if you are inside the inertial reference frame of the train is not moving at all. It is the surroundings that are moving. So the ball no longer has any horizontal velocity, only the vertical velocity you impart to it by moving your arm to throw the ball. Assigning frames of reference and understanding what they mean for the motion of objects is a big part of physics. And although some aspects of this kind of thinking seem obvious, they were not always well understood. Galileo was the first to rigorously describe relative motion after doing experiments in a moving ship. He found that if he dropped a ball while the ship was moving with constant velocity, it fell straight down, just like it did when the ship was stationary in the port. He then contemplated how a fish nearby would view the motion, with the ball moving forward as it falls, and how this differs from his own experience. He used these experiments to prove that velocity measurements depend on which reference frame you adopt.
Okay, so I think that that's another good example of how motion depends on your point of view, right? So when we describe motion, it's important to understand like who's observing it and what are they doing. Okay, so here are a couple of questions that I want you to think about and get some answers to. Make sure you have a good explanation. Be able to support whatever you come up with, and really think about what's happening with the laser on the train, and then compare that to what goes on with the ball on the train.